Welcome to Understanding Null Hypothesis Testing. Recall that Matthias Mehl and his colleagues in their study of sex differences in talkativeness found that the women in their sample spoke a mean of 16,215 words per day, and the men a mean of 15,669 words per day. But despite the sex difference in their sample, they concluded that there was no evidence of a sex difference in talkativeness in the population. Recall also that Alan Kanner and his colleagues in their study of the relationship between daily hassles and symptoms found a correlation of plus 0.6 in their sample. But they concluded that this means there is a relationship between hassles and symptoms in the population. This raises the question of how researchers can say whether their sample result reflects something that is true of the population. The answer to this question is that they use a set of techniques called inferential statistics, which is what this section is about. We focus in particular on null hypothesis testing, the most common approach to inferential statistics in the psychological research. We begin with a conceptual overview of null hypothesis testing, including its purpose and basic logic. Then we look at several null hypothesis testing techniques for drawing conclusions about the differences between means and about correlations between quantitative variables. Finally, we consider a few other important ideas related to null hypothesis testing, including some that can be helpful in planning new studies and interpreting results. We also look at some long-standing criticisms of null hypothesis testing and some ways of dealing with this criticism. The purpose of null hypothesis testing. As we have seen, psychological research typically involves measuring one or more variables for a sample and computing descriptive statistics for that sample. In general, however, the researcher's goal is not to draw conclusions about that sample, but to draw conclusions about the population that the sample was selected from. Thus, researchers must use sample statistics to draw conclusions about the corresponding values in the population. These corresponding values in the population are called parameters. Imagine, for example, that a researcher measures the number of depressive symptoms exhibited by 50 clinically depressed adults and computes the mean number of symptoms. The researcher probably wants to use this sample statistic, the mean number of symptoms for the sample, to draw conclusions about the corresponding population parameter, the mean number of symptoms for clinically depressed adults. Unfortunately, sample statistics are not perfect estimates of their corresponding population parameters. This is because there is a certain amount of random variability in any statistic from sample to sample. The mean number of depressive symptoms might be 8.73 in one sample of clinically depressed adults, 6.45 in a second sample, and 9.44 in a third, even though these samples are selected randomly from the same population. Similarly, the correlation, Pearson's R, between two variables might be plus 0.24 in one sample, minus 0.04 in a second sample, and plus 0.15 in a third. Again, even though these samples are selected randomly from the same population. This random variability in a statistic from sample to sample is called sampling error. Note that the term error here refers to random variability and does not imply that anybody has made a mistake. No one commits a sampling error. One implication of this is that when there is a statistical relationship in a sample, it's not always clear that there is a statistical relationship in the population. A small difference between two group means in the sample might indicate that there is a small difference between the two group means in the population, but it could also be that there is no difference between the means in the population, and that the difference in the sample is just a matter of sampling error. So similarly, a Pearson's R value of minus 0.29 in a sample might mean that there is a negative relationship in the population, but it could also be that there is no relationship in the population and that the relationship in the sample is just a matter of sampling error. In fact, any statistical relationship in a sample can be interpreted in two ways. One, there is a relationship in the population, and the relationship in the sample reflects this. Two, there is no relationship in the population, and the relationship in the sample reflects only sampling error. So the purpose of null hypothesis testing is simply to help researchers decide between these two interpretations. The logic of null hypothesis testing. Null hypothesis testing is a formal approach to deciding between two interpretations of a statistical relationship in a sample. One interpretation is called the null hypothesis, often symbolized by H0, and reads as H0. This is the idea there is no relationship in the population and that the relationship in the sample reflects only sampling error. Informally, the null hypothesis is that the sample relationship occurred by chance. The other interpretation is called the alternative hypothesis, often symbolized by H1. This is the idea that there is a relationship in the population and that the relationship in the sample reflects this relationship in the population. Although there are many specific null hypothesis testing techniques, they are all based on the same logic. These steps are as follows. Assume for the moment that the null hypothesis is true. There is no relationship between the variables in the population. 2. Determine how likely the same relationship would be if this were the case. 3. If the sample relationship would be extremely unlikely, then reject the null hypothesis in favor of the alternative hypothesis. Otherwise, fail to reject the null hypothesis and continue to assume that there is no relationship in the population. So, following this logic, we can begin to understand why Mel and his colleagues concluded there is no difference in talkativeness between women and men in the population. In essence, they asked the following questions. If there were no difference in the population, how likely is it that we would find a small difference of d equals 0.06 in our sample? Their answer to this question was that this would not be at all unlikely if the null hypothesis were true. Therefore, they did not reject the null hypothesis and concluded there's no evidence of a sex difference in the population. We can also see why Kanner and his colleagues concluded that there is a correlation between hassles and symptoms in the population. They asked, if there were no correlation in the population, how likely is it that we would find a strong correlation of plus 0.60 in our sample? Their answer to this question was that the sample relationship would be extremely unlikely if the null hypothesis were true. Therefore, they rejected the null hypothesis in favor of the alternative hypothesis, concluding that there is a positive correlation between these variables in the population. A crucial step in null hypothesis testing is finding the likelihood of the sample result if the null hypothesis were true. This probability is called the p-value. A low p-value means that the sample result would be unlikely if the null hypothesis were true and leads to the rejection of the null hypothesis. A high p-value means that the sample result would likely be likely if the null hypothesis were true and leads to the failure to reject the null hypothesis. But how low must the p-value be before the sample results is considered unlikely enough to reject the null hypothesis? In null hypothesis testing, this criterion is called alpha, and it is almost always set to 0.05 or 5%. So if there's less than a 5% chance of the result as extreme as the sample result, if the null hypothesis were true, then the null hypothesis is rejected. So when this happens, the result is said to be statistically significant. if there is a greater than 5% chance of a result as extreme as the sample result when the null hypothesis is true, then the null hypothesis is not rejected. This does not necessarily mean that the researcher accepts the null hypothesis as true, only that there is not currently enough evidence to conclude that it is false. Researchers sometimes use the expression retain the null hypothesis rather than fail to reject the null hypothesis, but they never use the expression accept the null hypothesis. The role of sample size and relationship strength. Recall that null hypothesis testing involves answering the question, if the null hypothesis were true, what is the probability of a sample result as extreme as this one? In other words, what is the p-value? It can be helpful to see that the answer to this question depends on just two considerations: the strength of the relationship and the size of the sample. Specifically, the stronger the sample relationship and the larger the sample, the less likely the result would be if the null hypothesis were true. That is, the lower the p-value would be. This should make sense. Imagine a study in which a sample of 500 women is compared with a sample of 500 men in terms of some psychological characteristic, and Cohen's d is a strong 0.50. If there were really no sex differences in the population, then a result this strong based on such large sample should seem highly unlikely. Now imagine a similar study in which a sample of 3 women is compared with a sample of 3 men, and Cohen's d is a small 0.10. If there were no sex differences in the population, the relationship this week, based on such a small sample, should seem fairly likely. And this is precisely why the null hypothesis would be rejected in the first example and retained in the second. Of course, sometimes the relationship can be weak, the sample large, or the relationship can be strong, the sample small. In these cases, the two considerations trade off against each other so that a weak relationship can be statistically significant if the sample is large enough, and a strong relationship can be statistically significant even if the sample is small. The table below shows roughly how relationship strength and sample size combine to determine whether a sample result is statistically significant. The columns of the table represent the 3 levels of relationship strength: weak, medium, and strong. The rows represent 4 sample sizes that can be considered small, medium, large, and extra large in the context of psychological research. Thus, each cell in the table represents a combination of relationship strength and sample size. If a cell contains the word yes, then this combination would be statistically significant for both Cohen's d and Pearson's r. If it contains the word no, then it would not be statistically significant for either. There is one cell where the decision for d and r would be different, and another where it might be different depending on some additional considerations. Please look for part 2 of this narration.